leave sound. Is that the one?
Yeah, it should be unticked.
Unclicked. Okay, I don't know if I did it.
Unticked. Well, no, maybe.
I don't think I can.
It's unclicked. Yeah, it's
Oh,
unclicked now.
Okay.
Oh, okay, good. All right, solve that problem. Okay, is it time yet? Oh yeah, we're late. So let me get this going. Our next speaker is, I'm not sure how to say your first name.
It's Tejas.
Tejas
Yeah, Tejas.
Kalelkar.
Yeah.
Sorry about that. Indian Institute of Science Education.
Yeah.
Take it away.
Okay. Yeah. Thanks, Frederick. So my talk is about an algorithm to identify hyperbolic manifolds from their geometric triangulations. And this is joint work with my students, Advait and Sriram. So to start with, let me just state this, what's called the homeomorphism problem. It's kind of the most basic question in combinatorial topology, which says that if you're given the combinatorial data of two triangulations of manifolds M and N, is there in fact an algorithm to determine whether M and N are homomorphic, where the input is just this combinatorial data. So from the combinatorial data of these triangulations, can you determine if the corresponding manifolds are in fact the same? So this is what's known as the homeomorphism problem. Now Markov showed that the homeomorphism problem in general is unsolvable, but in dimension 3, we have a lot more structure. So in particular, using the what's now called the Haken hierarchy, Haken gave an algorithm to solve the homeomorphism problem. And sort of the rough outline is that you start with a topological triangulation of the manifold, and then you cut inductively along incompressible surfaces, and you end up with cells, and then you just combinatorially compare the cell decompositions, and that should tell you whether the original manifolds are homeomorphic or not. Now, this, of course, is a gross oversimplification, and it's the full algorithm is fairly difficult to implement, and there are no known complexity bounds for this algorithm. Now, in dimension 3, of course, you also have geometrization, and using geometrization, there's a collection of algorithms. So there's an algorithm to check for irreducibility, an algorithm for the GHD decomposition, an algorithm to identify each of the 8 geometries, and then finally figure out which manifold it is within that geometry. So there are a lot of mathematicians involved in the different steps, and I've probably forgotten several names as well. But this is a collection of the people involved in this collection of algorithms. And again, this is an algorithm which is difficult to implement, and there are no known complexity bounds. And Sela, of course, for the hyperbolic situation, Sela gave an algorithm for recognition of torsion-free hyperbolic groups. And I'm mentioning Scott and Short over here because they recently had a paper where they gave an algorithm using only the statement of geometrization and not the ideas which go into the proof of the geometrization. But anyway, it's an algorithm that's difficult to implement with no known complexity bounds. In the direction of complexity bounds, the first result was by Kupperberg, who showed that the computational complexity of this problem is given by a function, which is a bounded tower of exponentials in the number of tetrahedra. So there is some function which is of the form 2 raised to 2 raised to 2, sort of this height of exponentials, tower of exponentials, raised to t, where t is the number of tetrahedra. He doesn't give an explicit height for this tower, but he just says there is some such function which gives the complexity for this homeomorphism problem. Now, if the question is to get an actual runtime bound on the algorithm for solving this homeomorphism problem, the first step, that's the most amenable way of going about it, is via something called Pacner Moves. So if K is a triangulation of an n-dimensional manifold, and D is a disk subcomplex of K, which is simplicially isomorphic to a disk on the boundary of an n+1 simplex, then a Pacner move on D replaces D with a disk which is isomorphic to the complement of D on the boundary of this n+1 simplex. So it's a lot to take in. It's easier to see this with some examples. So in dimension 2, for example, let's say you had a triangulation of a surface, then one of the possible Pacner moves is where you just take one triangle and you split it into 3, or the reverse process where you take 3 triangles which share a vertex and then you combine them together to give you one triangle. So it's basically a local move that you're making to this entire triangulation of the surface. And if you sort of want to follow this definition and what's happening, you're basically taking the bottom of this tetrahedron, replacing it with the top 3 triangles, or you take the top and replace it with the sort of the base of this tetrahedron. Another Pachner move in dimension 2 is where you basically take two triangles and you just flip the diagonal that you have between them. And these are the only possible Pachner moves in dimension 2. In dimension 3, you could start out with a tetrahedron and split it into 4 tetrahedra, or you go in the reverse direction, or you take two tetrahedra which share a triangle and you split it, sort of retriangulate it into 3 tetrahedra which share an edge. So these are the possible Pachner moves in dimension 3. And similarly, in every dimension, you have this finite collection of Pachner moves, which are local changes to the triangulation. Now, the reason Pachner moves are important is because of this theorem of Pachner, which says that if you start out with triangulations K1 and K2 of an n-dimensional PL manifold, then K1 is related to K2 by a finite sequence of Pachner moves. So only by doing sort of these local changes and finitely many such local changes, you can start with K1 and end up with K2. Okay, so there's a sequence of Pachner moves. And the reason it shows up in the context of the homeomorphism problem is because if I have a bounding function on the length of this sequence, on how many Pachner moves I need to go from K1 to K2, existence of such a bounding function is equivalent to solving the homeomorphism problem. And to see it sort of in one direction, sort of the more obvious direction, actually both directions are fairly straightforward, but to see it in the direction that we want, suppose we had such a bounding function. Then to show that you have, let's take you start out with triangulations Km and Kn of manifolds M and N, and with P and Q many n simplexes, and F n P Q is a bounding function for the number of Pachner moves needed to go from a triangulation of M with P n simplexes to a triangulation of M with Q n simplexes. Okay, so this is the bounding function, and this is given to us. So in order to solve the homeomorphism problem, what I would do is start out with Km and make a list of all triangulations that can be obtained from Km by at most F many Pachner moves. So this is some finite list of triangulations. And then I simply compare sort of at a simplicial isomorphism level, if any triangle in this list is in fact simplicially isomorphic to Kn. If any of them is in fact the same, then the manifolds are homeomorphic. And if none of them are the same as Kn, then the manifolds are not homeomorphic. So that is a sort of a simple algorithm to implement with explicit runtime bounds for the algorithm as well. So in this direction, Mijatovic has proved that for a large class of closed orientable irreducible 3 manifolds, there is such a bounding function, FPQ. And as expected, this function is a bounded tower of exponentials. So the bound that you get is 2 raised to 2 raised to 2. It's this sort of this whole tower of exponentials raised to the number of tetrahedra. And the height of this tower itself is an exponential. It's 2 raised to 162 times the number of tetrahedra. So on the one hand, it's great that we have an explicit bound. This is what we were looking for in order to solve the homeomorphism problem with runtime bounds. On the other hand, this is clearly not a practical bound in any definition of the word practical, right? It's a fairly large number. So the question we asked ourselves is there a sharper bounding function obtained for the number of Pachner moves needed to relate geometric triangulations of constant curvature n-dimensional manifolds? So on the one hand, the question is a little more general because we are asking in any dimension. On the other hand, we are placing severe restrictions. We are asking this question only for spherical, Euclidean, and hyperbolic manifolds. And furthermore, the input that we have are geometric triangulations, where the simplexes are all totally geodesic simplexes. So they're not topological triangulations anymore. So this is the context of the sort of how we came to such a question. And this is kind of what we've answered. So it's a long statement. I'll read through it carefully. So let M be a closed spherical Euclidean or hyperbolic n-dimensional manifold with geometric triangulations K1 and K2. Let K1 and K2 have P and Q many n-dimensional simplexes. Let capital lambda be an upper bound of the length of edges. When M is spherical, we require capital lambda to be less than or equals pi by 2. Let ing M denote the injectivity radius of M. When the dimension is less than or equals 4, then K1 and K2 are related by F many Pachner moves. And in general, their 2 raised to n plus 1 barycentric subdivisions are related by F many Pachner moves. And this bounding function F is a function of the dimension of the manifold, the number of top dimensional simplexes, an upper bound on the length of edges, and the injectivity radius. Okay, so the explicit function is it's basically a cubic polynomial in the number of n-dimensional simplexes. And if you look at sort of how it behaves with respect to n and capital lambda, it's 2 raised to n plus 2, n plus 1 factorial raised to 4 plus 3m. If you click on m, it basically expands again as a function of n lambda and the injectivity radius. Now, of course, the jarring note over here is a requirement of injectivity radius, because really we want something which depends only on the geometric triangulation. So the injectivity radius is not really known. Fortunately, for constant curvature manifolds, the injectivity radius can be bounded in terms of the volume and diameter. And both volume and diameter can be written down bounded in terms of the lengths of edges and the number of n simplexes. So we have this corollary of, which is what we were looking for, that you have a bounding function which depends only on the dimension, the number of top dimensional simplexes, and upper and lower bounds on the lengths of edges. Okay, so this is the bounding function we get for the number of Pacner moves needed to relate to geometric triangulations for Euclidean spherical or hyperbolic manifolds. Okay, and of course, just to compare it in dimension 3 with sort of this Nishitovic's tower of exponentials, if you start out with closed hyperbolic 3 manifolds, and if t is the total number of n simplexes, then the bounding function you obtain is something large constant times e raised to 83 times t into e raised to 3 times capital lambda. So it is, of course, still doubly exponential on the lengths of edges. So I wouldn't really call it practical still, but it's still far better than this tower of exponentials of height 2 raised to 162p. Of course, over here, the input is a geometric triangulation, while in the Nishitovic's result, the input is a topological triangulation. Now, also in dimension 3 for hyperbolic manifolds, the more interesting situation is for the cusped hyperbolic manifolds, while this result is for closed hyperbolic manifolds. And for cusped manifolds, the more natural setting is to work with ideal geometric triangulations where the vertices are essentially at infinity. So the lengths of edges are also infinite. So to get a corresponding result for cusped hyperbolic 3 manifolds, instead of working with capital lambda, which is a bound on the length of the edges, we work with theta naught, which is a lower bound on the dihedral angles of the tetrahedra in the ideal geometric triangulation of F. So we have another bound ft theta naught, where t is the total number of tetrahedra, theta naught is the lower bound of the dihedral angles. And again, we have some constant times t raised to 6 divided by sine theta naught raised to 12t plus something. So this is an explicit bound that we get on the number of Pacner moves needed to relate to ideal geometric triangulations for cusped complete hyperbolic 3 manifolds. So maybe just a couple of ideas which go into the proof. So we start out with 2 triangulations K1 and K2, and we want to go from K1 to K2 by a bounded number of Pacner moves. So the first step is to just sort of overlap K1 and K2 and look at the intersection. This gives us a common geometric polyhedral subdivision of K1 and K2. So the first step is to find a bound on the number of polytopes in K1 intersection K2. Okay, so we first bound the number of polytopes in this common intersection. And then the second step, which is just sort of heuristically argued over here, you want to really go from K1 to K2. What you go instead is from K1 to this common subdivision, and then from K2 to this common subdivision. And because Pacner moves are reversible, you basically get a sequence from K1 to K2. So this is what we're going to do. You first come up with a common subdivision with a bounded number of cells, and then you go from K1 to a subdivision of K1 and K2 to the same subdivision of K2, because it's a common subdivision, you end up with a sequence from K1 to K2. Now, in order to come up with a bounded common subdivision, so we start out with K1 and K2. These are triangulations of M. And if you just take the intersection and look at a barycentric subdivision, a priori, this may not in fact have a bounded number of convex polytopes. So for example, what's drawn over here is just a flat torus, and we have this red triangle. It's a flat Euclidean triangle. And then we have this blue triangle, which is also a flat Euclidean triangle. And as you can see, we can spin this blue triangle around the red one as many number of times as we need. And the number of polytopes in the subdivision can be made arbitrarily large, right? But this, of course, this kind of situation doesn't happen on the plane. If you just take 2 triangles, it's going to intersect in just one component. And that's because triangles on a plane are totally convex, where if you take 2 points on the triangle, it is joined by a unique geodesic, which lies entirely within the triangle. Now, fortunately, manifolds, of course, are not totally convex, but they're locally totally convex. So what we can do is start out with the given triangulation, and then take sufficiently many barycentric subdivisions so that the simplices become small enough so that they lie within a ball which is totally convex. So what I've written over here is just sort of the scaling factor. When you do a barycentric subdivision, what exactly does the diameter scale by? So if capital lambda is an upper bound on the lengths of edges of n simplex, then the diameter of the simplexes of the mth barycentric subdivision of delta is at most kappa raised to m times lambda, where kappa is the scaling factor, which is some number less than 1. Okay, and the exact number is written over here for the Euclidean, spherical, and hyperbolic situation. So these are calculated. And then, as I said, basically you just take m large enough so that kappa raised to m lambda is less than the injectivity radius. And therefore, all the simplices then become strongly convex, and therefore, any two of them intersect at most once. This allows us to bound the number of simplices in this common subdivision. Now, the second step in the proof is where the compact and the cusp situation vary. So the second step, I just sort of highlight the main thing which goes into it. So the main idea which goes into it is to understand how to go from a Euclidean triangulation of a convex polytope to a cone over its boundary. Okay, so the idea which goes into this is something called shellability. So we say that a triangulated n-dimensional ball K is shellable if there is an enumeration of its n simplexes such that delta I intersects all the previous n simplexes in an n-1 dimensional disk. So for example, if you look at this situation, this is not a Schelling sequence because 2 intersects 1 in just a point. So it's not a one-dimensional, it does not intersect in a one-dimensional disk, but this is just a bad sequence. If I sort of rewrote it in this way, then 2 intersects 1 in just a one-dimensional disk, 3 intersects 1 union 2 in a one-dimensional disk, and so on. So this, in fact, is a Schelling sequence. Now, if you have a Schelling sequence, so for example, this convex polytope is triangulated by a Schelling sequence, then this allows me to go from the convex polytope to a cone over its boundary. So what I could do is I start out with the first simplex in this Schelling sequence. I do a 1-3 move. I then look at the second one. I do a 2-2 move. Now the second one intersects the third one in a one-dimensional disk. I can again do a 2-2 move, 2-2 move. Now 3 of them share a vertex, so it's 3-1, 2-2, 2-2, and 3-1. So basically, if I start out with n triangles, by 8 Pachner moves, I go from the original triangulation to something which is a cone over its boundary. Now, when I came across this for the first time, I thought, of course, everything must be shellable. It's such an obvious property. And then I realized that way back in the 50s, Mary Rudin had shown that you have Euclidean triangulations of a 3 simplex which are not shellable. And then Licorice has a paper where he gives several triangulations of S3 which are not shellable, topological triangulations which are not shellable. So in some sense, the simplest triangulations may in fact be non-shellable. But I think the big breakthrough came around 2018. Advait and Benedetti proved that if K is a subdivision, everything's Euclidean, is a subdivision of a convex polytope, then its second barycentric subdivision does happen to be shellable. And this is what we use to go from sort of this convex polytope to a cone over its boundary. So sort of a very sort of rough outline of the proof in the compact situation is where you start out with triangulations K1 and K2 of the given manifold. If the dimension is more than 4, then you take as 2 raised to n plus 1 the barycentric subdivisions so that the link of each simplex becomes shellable. This is where Advait and Benedetti's result is used. We then take sufficiently many barycentric subdivisions so that each simplex now lies in a strongly convex ball so that I can intersect the two of them and get a bounded sort of a subdivision with boundedly many cells. And then we calculate the number of n simplexes in this common subdivision alpha k. And now our aim is to go from K1 to alpha k and from K2 to alpha k. And this is a step which I've kind of fuzzed over because there's less time. But the idea essentially is that you start out with an R simplex A in the original triangulation K. And I want to, so just to recall, I want to go from K to alpha k. So I start out with an R simplex A in the original triangulation K. I then look at the star of A in this subdivision. That's basically going to be kind of like a convex polytope. I use these results of Advait Benedetti in this way, and then I have this number of Pacner moves, which is in a controlled number of Pacner moves to go to a cone over its boundary. I do this for all the R simplexes, and then I vary my R from 1 to n. And so I start out with alpha k, the subdivision, and I end up with a barycentric subdivision of k, which is beta k. Okay, so basically at every step, I just look at a star of the R simplex, and by controlled number of Pachner moves, I go to a cone over its boundary. And I do this for all R simplexes. I vary R from 1 to n. And this allows me to go from the original subdivision to a barycentric subdivision of K itself. Okay, and barycentric subdivisions are very well controlled. So I can go from barycentric subdivision to the original triangulation as well. Okay, so I'll just stop over here. So just to sort of point out if you want to go back and refer to papers, the cusp situation is the first paper. compact situation is in the second paper. And the third paper just says that you can actually go from between two geometric triangulations via Pacner moves through geometric triangulations. So you don't really need to go via topological triangulations. The intermediate triangulations can also be made geometric. Okay, so I'll stop over here. Thank you.
Thank you. Let's thank the speaker. You can unmute if you want to. Are there any questions anyone wants to pose?
I have a question. Since you talk about the geometric barycentric subdivision, I know the barycentric subdivision, but I don't know the concept geometric barycentric subdivision. Is this related to the metric?
Yes, it is related to the metric. So actually, if you, in this paper, we actually spent some time defining what the geometric barycentric subdivision is, what a centroid is, and so on. So we kind of inductively define a centroid and so on. And this is actually a fairly good question. So one of the reasons why even a barycentric subdivision would not work on a general Riemannian manifold is because you need a lot of totally geodesic submanifolds. So there's a result by, sorry, I forget the name, but there's a result which says that if for every subspace of the tangent manifold, if you have a totally geodesic submanifold whose tangent space is that particular subspace, then in fact my manifold is of constant curvature. Okay, so if you have it's only in the situation of the constant curvature manifolds that you have a lot of totally geodesic submanifolds. And the reason that's important is because once you do a barycentric subdivision, you still want to remain a geometric triangulation. So you have a notion of a centroid, and then you have a notion of geodesics joining the vertices, and then the faces now should again be totally geodesic. So sort of every simplex should be totally geodesic. So you need a lot of totally geodesic simplices, and all of this does make sense in constant curvature manifolds. So there, it is some work, but you can define barycentric subdivisions using the metric.
So can I understand this geometric is defined piecewise in every simplex like that?
Yeah.
I don't know how you define this metric in your manifold.
Right. So for example, if you look at a Euclidean triangulation, right? So over there, I think you might understand. So in a Euclidean triangulation, what you simply do is you just take the, so V1, V2 to Vn are the vertices, and you just look at summation Vi by n. That's going to be some other vector. That's the centroid of this n simplex. Okay, and then you basically just look at cones with this as the coning point. So you look at, so you start to do it inductively. So actually, had one more slide which I had skipped because of lack of time. So this is kind of what's happening. So you see, you have the original triangulation, and then you look at a cone over its boundary, and then you take the star of the edges, you take the cone over its boundary, and so on. So this can be defined inductively as long as the notion of centroids and cones makes sense.
Okay, thank you.
Sure.
Other questions? Yeah, I wanted to ask a really elementary one. If you have two manifolds, and you have triangulations of them that you want to compare, how do you tell whether they're isomorphic or not? Is that part of what's the decision process?
So if you just want to check if they're simplicially isomorphic, then that's a purely combinatorial construction. So what you need is just some bijection between the vertices such that the corresponding subsets which correspond to simplices correspond to the corresponding simplices. So if you have some map phi, and if V1, V2, V3 is a triangle over here, then phi of V1, phi of V2, phi of V3 should be a triangle over there. So that's just simplicial isomorphism.
Okay, but all right, well, I think I'm running out of time. So let's thank the speaker once more, and